Welcome to another lecture and the beginning of a new arc of the course. So we've gotten through all of the root finding stuff. We're going to be starting with something fresh here, and it is a topic that is, I don't know, it's kind of fun. When I was a kid, I really liked numbers. I liked to count. I like to, I don't know, waste all sorts of time. Like I would literally take a notepad and write down lots of different numbers and today I would say like, oh, I'm counting by 13s today, 13, 26, 39, and I would write until I got to like, I don't know, 1,000, and then I get tired and so on. And so one of my favorite sorts of things, like coloring books, were so boring. I don't know. I do like them now, but um, the kind of activity book I liked as a little kid was connected dots. Because connected dots involve numbers, and then you create a picture that kind of emerges once you've got that. And I like to call this section of the course grown-up connect the dots, because that's essentially what we're going to be doing. We're going to be talking about interpolation. So given a series of points, can you find a curve that passes through them, or that gives some sort of relationship? So we're going to be talking about that over the next several lectures, and I hope you enjoy the show. So why don't we get to it and start into the notes. So we are talking about curve fitting and what's called polynomial interpolation. And let's go through the notes together. So suppose we were given a set of data points and asked to find a relationship describing that data. So here you can see just a whole bunch of points, and there might be lots of different ways to do that. So right now, we've really only started with the idea of like Taylor series as an approximating sort of method. You know, if you have a curve, then you might be able to approximate that curve using a Taylor series. Yeah, so a couple of different things here, right? These points that we're talking about here don't necessarily belong to any particular curve, but also the problem with approximating with a Taylor series is that we know that it's perfectly accurate at the center point of the series, but then an approximation is going to deviate, like become further and further off the further away that we get from that center point in general. So in addition, how do we incorporate all the information? If we know that, right, if we know that the data that we have might be accurate, not just at this point, but also at this point, and also at this point, and also at that point, and also at these points, and so on, I can't have a Taylor series that kind of hits all of them at the same time and is perfectly accurate at each one. So yeah, we need some different kinds of tools here. But there are methods of producing polynomial functions that remain close to a given function f, even, where's my cursor, even away from a particular center point. Polynomials provide us with a method of connecting points because it can be proven that given n points, if you have n points, we're talking about 2 dimensions here, where you know, x1, y1, x2, y2, all the way through. So we have at least 2 points here, with none of the different x values being the same. There has to exist a polynomial of degree n minus 1, called an interpolant, that passes through all of those points. Now this polynomial here is I don't know, this graph here is made by paint. This is actually not a polynomial interpolant. Polynomial interpolants do tend to go up and down quite a bit. Well, we're going to talk about some issues associated with these in a second, but it captures the idea of what's going on. That we get a single curve that might be a high degree polynomial that hits every single one of those points along the way, and therefore is a curve that incorporates all of that data. So this concept can be useful when working with complicated functions. Okay, so it really depends on what you want, though, and there are a few different ways to go about doing this. Having a quadratic or a cubic approximation of a function might be precise enough for some applications. Working with a simpler polynomial might be less computationally intensive than working with a high degree polynomial, but maybe I need a high degree polynomial to exactly go through every single one of those points. So there's some give and take there. A related method, we're not going to cover it explicitly in this course, but one thing that you've probably already seen before and might be studying in statistics courses right now is what is called least squares. Least squares approximation. And with this method, the goal is basically to find a curve of best fit that follows some kind of proposed relationship. So that essentially means that you're finding the line segment or the parabola or whatever the degree of polynomial you're interested in, or maybe it's some other kind of function for more detailed applications and so on. But essentially you're trying to find the curve that minimizes the overall distance between all the different points that you're interested in and the curve itself. So it actually becomes a pretty complicated optimization problem that leads to some formulas that you can use to figure out what the slope and what the y-intercept and all that stuff should be for a linear term, or what any coefficients of more complicated expressions might be. So in general, curves like this do not pass through any of the given data points, but instead they're chosen to minimize the total error considering all of those data points. These are really useful curves. But as I said, many of you are already learning kind of how to construct these things in other courses. So I just want this to kind of be a background of some things that we could have talked about here in related news. But it's not going to be an interpolant specifically because it doesn't necessarily pass through all of those points precisely. But I'll let other statistics courses and other courses be flesh out that knowledge a little bit more. Okay. So another useful place for these concepts, I have like this little point at the bottom here, is perhaps, students always want to know where this stuff can be useful. And for different kinds of modeling, for different kinds of you're trying to establish a relationship based on particular experimental results. Perhaps you're in a lab and you're doing certain measurements over time and you want to show that something has an exponential or a linear relationship. You can see how tools like this can be really useful. You're taking data that might have a little bit of error, but you can find a function that either passes through or close to those points. So there's some really useful stuff in this section. Okay, the topic that we're going to center on for the rest of this lecture is an introduction to Lagrange Interpolation. After this, I think I'm going to do 2 other really short videos on how to code this and on issues with Lagrange Interpolation before we get into some other methods as well. So, the problem we're going to specifically center on here is, given some data, like the locations of a number of points, find a polynomial that fits that data. The Lagrange Interpolant gives us a pretty simple way of doing that. And I think it makes a lot of sense when you think about it. So we're going to consider the problem of building a polynomial first that passes through just 2 points. And we're going to scale up from there. Okay, so suppose we have 2 points. We have an x1 and a y1 and an x2 and a y2. And we could just draw that for funsies over here and see what that looks like. I don't know where these are. We do need for this, and I said this in the original problem, x1 is not equal to x2. So I need 2 different x values, or else of course the polynomial can't hit both of those at the same time, because it's not going to be a function that does that, at least not one of x. So if we have 2 points, we're talking about, maybe it's this point right here, maybe this is x1, y1, and maybe this here is x2, y2. Okay, with 2 points, I think it's pretty clear that there's going to be a unique straight line that connects those 2 points, right? There's exactly one straight line, which is a first degree polynomial that does the trick. So my colors are swapping around here. A unique straight line passes through both of those points. So what we're going to do is something very, I don't know, it's a simple idea, but it's very particular. Okay, we're first going to define 2 basis functions. And those basis functions are going to be given by the following. So we're going to call them L1 and L2. L for Lagrange. And we have L1 of x equals. Here's how it works. Take x, subtract x2, and in the bottom, put x1 minus x2. L2 is going to be the same thing, but I'm going to kind of swap things around. I'm going to take x, I'm going to subtract x1, and then on the bottom I'm going to put x2 minus x1. Okay, so the Lagrange interpolant is then a combination of the two of those things. And it's a combination that basically takes both of them, multiplies by their own y values, and then adds them together. So if I write this all out, we would get here y1 times x minus x2 over x1 minus x2 plus, and then it's y2 times x minus x1 x2 minus x1. Okay, this might seem like pretty weird for a second. Like, why would we want to write something in this way? Maybe it seems more complicated than it needs to be, or something like that. But I want to play with this for a little bit, and you'll see pretty quickly, I think, why this is going to work out. So check this out. I think I'll go into more detail on the next page, but I kind of want this here. Imagine that, if I call this a new function, p of x, this here is nothing more than my L1. This here is nothing more than my L2, as we have them defined above. This is a function of x, and so I should be able to plug in different values of x, agreed? So I want to just play for a second. Imagine if I put in x equals x1. If I put in x equals x1, I would get here an x1 minus x2 over x1 minus x2. And you see what happens? I would get that ratio becomes 1. This whole thing is therefore 1 times y1. And at the same time, if I put x1 in here, x1 minus x1 is 0, and this thing dies completely. So you see, if I put in x1 into a polynomial of this form, I end up with y1 times 1 plus y2 times 0. In other words, when I put in x1, I get a y1, which is what I need, right? I need a line that goes through x1, y1. Let's do the same thing with x2, so you can kind of see the symmetry in that. If I was to put x2 in here, I would get x2 right here, and I would get x2 right there. And in the first ratio, you see x2 minus x2, that's 0, and that's going to kill this term. And now over in the second one, I would get x2 minus x1 over x2 minus x1, and that is 1. I would get 0 plus y2 times 1. In other words, when I plug in x2, I would get out y2. And that's, again, what I need. I need x2, y2 to be a point that's on that curve. So that is kind of the justification for building this whole thing. Let's fill in some blanks in the next page. So we see that L1 of x1 is equal to 1, while L2 of x1 is equal to 0. That is, if I put in x1 and I put in x1, that makes sure that p of x1 always yields y1, which is what we need. And similarly, when I put in x2, I get in a 0 right here. I get in a x2 minus x1 there, so I'm going to have that second ratio give me 1. And of course, the sum of those is going to give me y2, like we demonstrated before, as it needs to. So essentially what you're doing is finding just the right combination, just the right linear combination of those basis functions to lift up the resulting line segment to pass through those 2 points, which is pretty cool. Okay, exercise time. Find the Lagrange interpolant for the points minus 1, 3, and 5, 4. Why don't we start by calling these some useful names here. So let's be x1, y1 right here, and this could be x2, y2 right there. Okay, and let's remind ourselves of the form of this. We need a p of x to equal y1 L1 plus y2 L2. And what the heck are the L1 and the L2? Well, let's remember from before. So the L1 is equal to x minus the other one, x1 minus the other one. L2 is equal to x minus the first over x2 minus x1. I'm just going to go verify that that's the case. And I think that's what it is. So I think we're good to go. And let's put it together. So let's create the basis functions. It's really straightforward, I think. I think it makes some sense. it looks like L1 of x is going to equal, okay, x minus the other one. So x2 was 5. And then I'm going to take x1 minus x2. So that's minus 1 minus 5. Okay, L2 of x is going to equal x minus the first. So that's x minus minus 1 over the first one, 5 minus minus 1. Cool, that's what it should be. So, if I put together my P of x should be our y1, L1. y1 is 3, so 3 times that first one, x minus 5, over minus 1 minus 5. And then I'm going to add the second one, which would be, let's see, y2, L2. That's going to be 4. And then over here we have x plus 1, it looks like, over 5 plus 1. And this looks like the form that we need. Of course, we can simplify this down. So this is just y1, and this here is just y2. No surprises there. This is L1, this is L2. And note that the bottoms of these different basis functions are always just numbers, so you can simplify them pretty easily. So let's just take some time to do that here. It's nice for a first demonstration. This is 3 over negative 6, so I think this works out to negative a half x minus 5. And over here we have 4 over 6, so that works out to 2/3 x plus 1. And heck, we could really just simplify this all the way down. So why don't we do that, just for funsies? Minus a half x plus 5 halves plus 2/3 x plus 2/3. So this is going to give us P of x equals, let's see here, minus a half x plus 2/3 x. Mental math, totally. 2/3 is 4/6 minus 3/6 is 1/6. So I think we get 1/6 x. And then, fun times, 5 halves. 5 halves is 15/6. And if I add 4 more 6, I think we get 19/6. Like this. So this would be our unique first degree polynomial straight line that connects those two different points. Why don't we just graph this out so we can see it in front of our eyes and believe it? So minus 1, 3, and 5, 4. Minus 1, 3, and 5, 4. I'm just going to tilt this graph to be a little bit skewed so we can see this easily. Minus 1, 3. So that we can say that's about here. And 5, 4 would be 1, 2, 3, 4, 5, and one additional step up right there. Nope. There we go. This is about 5, 4. Very rough here, but I just want to demonstrate a point. If I draw the line, no, I want a straight line. Sorry about that. That does not pass through it. Sorry, I want this one right here. I thought drawing on a board in person was hard enough, but here we are. There's the line. There's the line. I like that line. So, let's see here. Check this out. We see that this straight line definitely has a mild slope, so 1/6 x seems like a really good likelihood that this is right. And then it looks like the b, the y-intercept, is 19/6, which is, what, a little bit more than 3. So this makes perfect sense. So this would be, maybe I'll write this in blue. This is the line P of x equals 1/6 x plus 19/6. And it looks like the unique straight line that goes through. And as I said before, our final answer is nothing more than just the right linear combination of those two basis functions. So they provide a really useful kind of building block to make the right polynomial. So that's the basics. The question is, how can we extend this to a larger number of different points? So we can extend this process, and I think that once we gain an understanding of what's going on there, we can kind of gain some confidence about higher degree polynomials and the formula that we have to use. So we have to be able to build higher degree polynomials that pass through a greater number of data points. So we're going to take our knowledge from before, we're going to try to create what look like bigger basis functions, heftier basis functions, but they're not hard to get your mind around if you think in the same sorts of way. So we have, this time, n data points, x1, y1, x2, y2, all the way through xn, yn. What we want to do, in the same sort of way as before, is define a basis functions that are equal to 1 at one of those xi values, but 0 at all of the others. And then we can lift up a combination to be the right combination to fit all of them, kind of like we did before. We can actually do this using the following. This is really, really scary notation. I don't want you to freak out about it too much, but this is product notation. So kind of like summation notation, except you're multiplying things instead. And I wanted to emphasize that this has exactly the same structure as what we've already seen. It's just that we have multiple things multiplied in the top and the bottom. Notice that it's a fraction still. We have this this division that's right there. And what we're going to do here is the ith L function, the ith basis function, is going to take the product of all x minus xk, where each of the different k's here are the different x values that aren't the ith one. So the first basis function is going to include x minus the second x value, x minus the third x value, x minus the fourth x value, but not x minus the first. Okay, we're going to divide that by another product, and that product is going to be the first x value minus the second one, the first x value minus the third, the first minus the fourth, and so on. In this way, we can construct something that's parallel and analogous to that, that opening example that we did. And it's really not that much harder. We're going to do an example and you'll see. And you can get a feel to see that these formulas create the very same sort of spirit of those basis functions that we saw in those first examples. So it's kind of fun to test these out and test out plugging in, say, one of the x values and watch the whole thing collapse down. But imagine, right? This defines a function of x. If I were to plug in x, the ith x value here, then I get exactly the same thing on top as I have on the bottom, and everything cancels and gives me 1. But if I plug in any of the other x values, the second one, the third one, the fourth one, that appears right here as well, and so one of the different factors is going to be 0, and that's going to force the whole product to be 0 as well. So you can see that the same sort of structure is there as in our opening example. So it looks a little bit cumbersome, but I promise it's not too hard. And then once you've got all of those different basis functions, you take a linear combination of all of them, lifting up each one to its own designated y value. So you take yi times li, and you sum them all up, and then you're done. So let's do this. Let's put together a Lagrange interpolant that connects these 4 different values. Nodes are often used just to indicate points, so don't be afraid of that word at all. I don't mean anything super special by this. Let's give these things some names. I like to name my points before I play with them. x1, x2. Nope, that's not what I want. I want x1, y1. That's really what I want. x2, y2. x3, y3. Just going up and down so I have room for all of them. x1 or x4, y4. Okay, we're going to need 4 different basis functions. And let's write them all out. So we need 4 different basis functions. Okay, the first one, L1 of x is going to equal. Now let's think of how this went. I need to skip over the first for this one and instead go x minus x2, x minus x3, x minus x4, and on the bottom I put x1 minus x2, x1 minus x3, x1 minus x4. Okay, we have all of that data, so that's not going to be too hard. This is going to be x minus, and then just be careful about, it's very easy to write down the wrong thing here, so take a little bit of time, but x minus 3, x minus 5, x minus 7, And on the bottom, we're going to have here x1 minus x2. So 2 minus 3, 2 minus 5, and 2 minus 7. So it's almost like a pattern, right? A poem of some sort. X minus 3, x minus 5, x minus 7 over 2 minus 3, 2 minus 5, 2 minus 7. Create a song and get back to me on that one. I don't know. Do whatever you need to do to remember this or be comfortable with it at least. Of course, the bottoms are just numbers, and we could multiply those together. So this is just doing some quick math here. This is minus 1, this is minus 3, this is minus 5, and the multiplication of those three, I think it's negative 15. So we get here negative 1 over 15, x minus 3, x minus 5, and x minus 7. So this is our very first basis function. I want to point something out here. It looks like each of our basis functions for this example are going to be cubic functions, right? We have an x times an x times an x. And we're going to have the same sort of structure for L2, L3, and L4. When we take a linear combination, we're going to be adding together some x cubed terms, x squared terms, and so on. The result is that we're going to get a cubic. And it's a unique cubic that goes through those 4 points, which is kind of what we led with, right? To get to put a polynomial that goes exactly through n points, it needs to be an n minus first degree polynomial, is what I wanted to say. Okay, that's one down, but we need 3 more, so let's just do them. L2 of x will be, just to give you a feel for it, I'll do one more time here, x minus x1, x minus x3, so skipping over again that second one, x minus x4, and then we put that over x2 minus x1, x2 minus x3, x2 minus x4, and we could put that together without too much trouble. This is going to be, what can we really do here? X minus the first x value was 2, x minus 5, x minus 7. The bottom is going to be, it's x2 minus x1, so x2 is 3, so it's 3 minus 2, 3 minus 5, and 3 minus 7. So it looks to me like we're going to get here, again, let's do some quick math at the bottom, 1 times negative 2 times negative 4. It looks like the result's going to be an eighth, right? 1/8. X minus 2, x minus 5, x minus 7. Okay, you start to get the feel for these. And so I'm just going to try to avoid using the formula for the next one, and we'll see if I don't screw up. But L3 of x, so I'm just going to write similarly. L3 of x is going to take x minus x1, x minus x2, x minus x4. So let's try this. X minus the first, x minus the second, and x minus the fourth over, and then the third minus the first. The third minus the second, and the third minus the fourth. And this will work out to 3 times 2 times, negative 2 is, let's see here, 3 times 2 is 6 times a negative 2 is going to be negative 12, so I think it's minus 1/12. Correct me if I'm wrong, but I think we're good. X minus 2, x minus 3, x minus 7. It's a little bit of a slog, but it's kind of cool that we have the tools to be able to put this together without too much problem. And L4, finally, is going to be x minus 2, x minus 3, x minus 5, the first, second, and third, over 7 minus 2, 7 minus 3, and 7 minus 5. And you work that out, and I think it turns out to be, 5 times 4 times 2, yuck, that's a lot. 5 times 4 is 20, times 2 is 40. Well, I guess it's not that bad. So 1 over 40. And then x minus 2, x minus 3, x minus 5. Just like that. So I think that, right, it's an intimidating formula at first to get these, but it's not too bad. This is not the answer, right? Our answer our answer is, to actually get the polynomial, I need that linear combination. So it's going to be p of x equals, and then we need the first y value, y1, is 2. So notice that the y values don't come into play until the very end here. So 2 times, I'll just write down L1. You could write out everything here, but it gets very cumbersome, and we already have these things written down. So 2 times L1, negative 1 times L2. So I'm going to write minus L2. I think the next one was plus 10 L3, and I think the last one was plus 0 L4. And just verifying that, and I think we're good. You could write this all out if you wanted to, but it's fine if you have everything out in the page. I'm fine with you presenting your final answer in this sort of way. Notice that because L4 has a height of 0, it doesn't even factor in, and you could finish just like this. Okay, so all of our different basis functions are different cubic functions, as I was saying before, and the final answer is a linear combination of those, which then presents itself as a single cubic function. Okay, so that pretty much puts it together. That's about as far as Lagrange polynomials go, but we have a little bit more to talk about here. So let's bring it in here. This is a really cool, quick method for coming up with polynomials. But there are some issues with it. We're going to talk about those in a couple of lectures, I believe. And there are also a couple of other interesting adaptations and extensions and extra things you can do with interpolation that we're going to get into as well. But before we talk about those things, we will be talking about how to code this, because it can be a little bit interesting. There are a couple of considerations to make. So I'm going to do a little video on that as the next thing. So coding is going to be the next lecture. I sure hope you join me. And until then, I bid you all a fond farewell.